Welcome to Breadboarding. In video 13, what we're going to be doing is taking the existing NanoComp and adding a serial port to it so we can hook it up to the USB port on a modern computer. In the subsequent video after this, we'll then be writing the software to test the input and output signals going from a computer down to the NanoComp. And in the video after that, we'll then look at extending the existing NanoComp monitor to be able to save and load files from the PC. In particular, this will allow us to make assembly language output in the form of the SREC format, which is a format for representing binary files from Motorola. And we'll use the SREC format to be able to download, compile programs down to the NanoComp and be able to run them. So we're going to look at our block diagram. I'm just going to quickly go up to so what we're going to do now is to add the serial port. So this could be wired into the data bus. There's only one address line used by the serial port, and we're going to add the serial port to our address decoder at the 5000 range on the Y5, the output Y5. This means when we want to address the serial port, we can use any of the 5000 addresses. In reality, there's only 5000 and 5001 are the only ones we actually need to worry about. Then we need a clock. There are some particular crystals that are designed to divide down to create the standard baud rates. The standard baud rates originated with about a 300 baud was the original starting point. So what you'll find is a lot of these are multiples of 300. At some point in time, when you get to the 115,000 and 57,000, there are different multiples. So what we'll see here is if we use the 3.6 megahertz clock, the built-in dividers that the serial port asynchronous communications interface adapter, as it's known in the Motorola datasheet, is able to divide by 16 or 64 according to the control register. The 3.6 megahertz crystal feeding the serial port can be divided by 16 to give 230 kilobits per second, or by 64 to give 57.6 kilobits per second. That's probably going to be a little bit fast. If we divided that clock by 2, then we'd get down to 115 kilobits per second. But I think to start with, what we probably want to do is to work down at the standard default speed for a lot of ports is 9600 baud, which is reasonably slow but fast enough for the NanoComp. You think we've only got 4 kilobytes of RAM, and at 9600 baud, that's approximately about 1 kilobyte per second. So it's only going to take a couple of seconds to transfer the data. So in order to do this dividing, a bit of an awkward number, divide by 6, but there is a particular chip, a standard logic TTL gate, which is the 74LS92. And that has built-in divide by 2 and divide by 6 on the chip. Divide by 6 or divide by 3 is quite awkward. You need a specific arrangement of flip-flops to be able to do that. But this chip already has it. So what we're going to do is use this 74LS92 with divide by 6. So that should mean that with the built-in divide by 16 or divide by 64 in the serial port here, we should be able to get 38K or 9600 baud, which are two reasonable speeds. 38K is quite fast, 9600 baud is fairly standard. Then as far as connecting the serial port to the PC, in days gone by, we'd have used an RS-232 interface. Now, RS-232 uses plus or minus 12 volts, which is quite awkward to get. And there are specific chips you can get that generate the signals for this, but it's a bit of a waste of time given that we just want to plug this into a USB port. So what I'm going to do here is use a standard USB to TTL adapter. This sort of device is used for programming Arduinos and the like. If you have this is an example, and they all tend to use the same FT232RL chip. That's a fairly standard chip for providing USB to serial output. And so we'll be looking at this particular chip in a bit more detail as we come to set it all up. But this basically allows us to plug those 6 lines into the breadboard, and then we can plug this into PC using a mini USB connector, and we can then just access the NanoComp through a serial port on the computer. Okay, so we're going to use our 3.6 megahertz crystal and the divide by 6 here. So we're going to use that, and then we're going to be using this TTL to USB serial adapter. They normally can cost a couple of pounds a time, and that's going to connect to the PC USB port, where we'll be using a virtual communications port or COM port to connect to that. So we're actually going to be using the Motorola MC6850 ECIA, Acacia, however you want to say that, a synchronous communications interface adapter, sometimes also known as a UART. This has a number of registers in it. There are generally 2 addresses it uses, and it uses the read-write control lines to determine whether we're reading or writing to the control and status registers. So we have a data port for sending data or receiving data, and we have a control port for setting control register values or reading the status register to determine what the current state of the serial port is, whether there's data available for reading or whether the serial port sent data and is waiting for some more data sent. There's also the clock divide, can divide by 1, 16 or 64. The data sheet on the chip means that divide by 1 probably is going to be too fast, so we're probably not going to use divide by 1, but divide by 16 or 64 allows us to get a reasonable range of speeds. It is possible to get interrupts to the NanoComp on the transmit data register empty alert. So this basically means it sent the data and it's ready for some more, or the receive data register full signal. That means we've received data, it's ready to collect. So we could use interrupts to do that. If we were writing software that was going to go off and do lots of other things at the same time, we would probably want to use interrupts. But because our send and receive functions in the monitor are only doing this and not doing anything else, we can just poll these registers for the values until such time there's something to do. So as I said, there's no need for our RS232 signals, the plus or minus 12 volts, and it's actually an FTDI compatible serial TTL adapter, and the FT232RL is a standard chip which is used in most of these adapters. The virtual COM port on the PC uses this particular driver. Again, this comes from FTDI. The signals that we need to connect between the USB port adapter and our serial interface, because both of these devices are what called data terminal DTE device. There are DTE devices and data communications devices. So a data communications device would be, for example, the old-fashioned modems that would use the telephone line. But when you're connecting a DTE to a DTE, you do need to switch the lines over. So the transmit and receive lines need to be crossed over. So the transmit on one goes to the receive on the other, and receive on the other goes to transmit. Ground will go to ground because we need to have ground. If we plug in the 5 volts, then the serial adapter will try and power the whole of the NanoComp from the PC USB port, which we don't really want to do. So we won't be connecting 5 volt line. And these other hardware handshake control lines, the clear to send, request to send, are connected to the opposite signals. So that allows the 2 computers to control handshaking at the hardware level. So if one's not ready, it can signal to the other to stop sending data. The data terminal ready is the equivalent of request to send, and that's connected to the clear to send. So basically we've got the hardware handshaking signals connected to its opposite on the other side, and the receive and transmit are connected in a crossover connection. In days gone by, this would be known perhaps as a null modem configuration, whereby you're simulating the connections the DTE device would have connecting up to a modem. So what I'm just going to do is to make a little bit more space on the top breadboard up here. So we've got a bit more space for putting the serial port and the clock in there. I should have perhaps done this a little bit earlier when I did the design, but so just going to move everything down by about 10 holes, I think. So just moving the reset non-maskable interrupt lines, shift the chip down, and then we'll move all the lead going off to the keyboard, hook up the power, then we'll move over the other interrupt lines, address lines, reset, and all the data lines as well. And finally, you've got a last couple of control lines and the chip select hooked up, and just modify the chip enable connection. So that should work. Let's just plug in the phone. We just need to remember to do our power here. So this is one of the challenges with power. All gets a little bit tight down the end here, but for the moment we'll just plug this in here. Yeah, what I'll do when we add some buffer chips down here, we'll completely rewire all of the power distribution, and that will sort it out for the long term. So let's just make our powers there. We've got that there, and we're just going to try and power this on. Try that again. Go. There we go. A, B, C, D. Reset. Memory. 7, 8, 9, E. Okay. 4. Memory. 1, 2, 3. Yep. So everything seems to be working okay before we. So what I've got here is the KiCad schematic of the NanoComp, and what I've done is I've moved the peripheral interface adapter over a little bit on the diagram. This is also as reflected on the breadboard. And what we've done here is add the 6850 here, along with, this is the clock chip. So rather than getting a separate crystal oscillator with capacitors and perhaps an inverter to generate the clock, it's a lot easier just to use the pre-built 4-pin crystal clocks here. So all we need to do is hook up the ground +5, and then we get a 3.6864 megahertz signal out of that. The 74LS92 has 2 clock inputs. Clock A input is to do the divide by 2. So clock A goes in there and comes out of QA, and then we would fend QA into clock B if we want to do divide by 12. But because we want to do divide by 6, we're just going to feed our 3.6 megahertz signal into clock B, and coming out of D will be our divide by 6 signal. And depending on if we divide by 16 in the configuration of the serial interface, we'll get 38.4 kilobits per second or baud. And if we use divide by 64, we'll get 9.6 kilobits per second or 9600 baud, which is pretty much the standard. We can see here with the interface, this is the TTL USB serial interface. So we've got ground, clear to send, VCC, 5 volts, which we're not using, transmit, receive, and data terminal ready. And the way how these are wired up, the data terminal ready, we can see is wired up to clear to send. And if we see request to send, should be wired up to clear to send, clear to send. It's not quite as easy to follow the diagrams as it is in Fritzing, but it's good enough. So I've printed these out and I'll be working off this layout. Then there's just a few other things we need to worry about. So the E signal is the clock signal, which determines when the chip reads the values from the data bus. Read-write is used to determine which of the status register or control register is being used. Data carrier detect is a line that used to be used for modems when there was a carrier signal on the modem. We're just going to tie that to ground because then it's always enabled. And then we see here that the transmit clock and receive clock both can be tied together and driven from the same clock signal. Some very low baud rate sometimes was a different baud rate. For teletypes had, I think, 110 baud for output and a lower baud rate for input, 75 baud, I think, for input. It was something like that. The transmit and the receive clocks are going to be identical here. Then we've got the transmit data and the receive data, and you'll see that transmit data, it should be going to the transmit here, it should be going to receive, and transmit data here should be going to receive here. So we've got the crossover of the signals. And what we'll be able to do later is to put the logic analyzer on here. The logic analyzer does understand serial communication, so we should be able to see the data going backwards and forwards between the chips and the PC once we've got everything set up and the program's written. What we're going to do now is to start laying out the chips on the board. I'm not going to do a Fritzing layout for this because now that I've got enough space on the breadboard, then we shouldn't have too much trouble laying this out and hooking up. And again, what I've done here is I have made the chips layouts in their physical pin. So you can see here, pin 1 is actually at the top here. We just need to be careful that when we plug in this chip, that pin 1 is at the top here, and you see 1, 2, 3, 4 divided to 12, 13 to 24. So because I've made the schematic pin out the same as the physical pin out, it does mean that when we're plugging these in breadboard, then the physical layout is going to be very similar to the layout here. So we're going to end up with quite a few yellow cables, for example, going from here over to where the serial adapter is going to plug in here. So we do need to leave at least 6 lines or so between these two chips so that we can plug that in and hook all the wires in. Okay, so what we're going to do now is to go to the breadboard, put some chip labels on our chips and start laying things out. What we're going to do now is just have a quick look at the components. So as I said earlier, we've got this USB to TTL program uploader. So this is the Future Technology standard sort of chip, which is used for a lot of these USB ports. I'll be using one of those. We've then got our Motorola 6850P, which is a standard sort of serial port. And we've got our 74LS 92, which is our divide by 12 or divide by 6. This is a 4-pin clock oscillator, and this one is designed to run at the 3.6864 megahertz. So that's one of the sort of frequencies that divides down to 9600 baud and other frequencies and things. And we've got a couple of decoupling capacitors, and as usual, the various jumper cables for ground and 5 volts. And then we're just going to put the address labels on. Yeah, that is connected to that pin there, so that's that one. Let's do the right. Okay, so that's that one. Then finally we've got our, okay, so those are the chips and the capacitors. So now what we need to do is to plug them in and wire them up. So we've got our board back. You remember we've moved the PIA over to the right here a little bit, just moved it down about 10 holes just to give us a little more space to work with here. Now the main thing that we need to be aware of here is that we have pin 1 on the right hand side of this particular chip, so we need to turn that round to be that way. And we do need a couple of wires to go between here, so we don't want to be going straight up to the side of that one there. So we're going to put this in. Let's just make sure that we're going to need more gaps on this side, in fact. So I'm going to put just 2 holes on this side as we're wiring in the data and address lines, and then we're going to leave more space on the other side there. So I think we'll just move it up 1. Just make sure that our VSS, VCC, and the other chip lines not quite lining up there, but I don't think that's a big deal. Perhaps we just move it up 1, and that means that chip select 0, chip select 1 can both go to power rail there. VCC, VSS can go to power. So now we then need to allow for 6 pins for our card here. So if I just give it a gap there, so let's say, and then we're going to put this at the top left here, sorry, and see, do we have sufficient space? So pin 1 goes to the top up here for clock B again. So yeah, I think we've got enough space here. So we'll leave a couple of holes there, and there's a couple of holes there. So everything should be laid out okay. So what we're going to do now is just to plug this one in. Here we go. Might just need to get the pins to be a little splayed. I'll just push the pins in, make sure pin 1 is still on the right here, and we said chip select 2 was going to be lining up there, and we want to make more holes on that side. There we go. That plugs in quite neatly. This one's got enough space, and then we're just going to squash these pins down. Little splayed. Bend those down and make sure we've got it the right way. Yep. Okay, and then this one's in as well. So that looks like it's a reasonable layout. What I will do is get a label printer to do the labels for the various pins on this thing, just so that when we're hooking it up we don't make any mistakes. But as I normally try and do, let's just hook in the power first. So we'll do ground first. The VSS is ground. In. We'll do 5, which is VCC. That's going in here. Too long, but doesn't too much. Right, and we'll do the same for this one. So this is a little unusual in that the ground and 5-volt pins are actually halfway down the chip. Both of those, so short wire for VCC. And then ground is going to be a long one for this one over here. So this pin is, yes, it's on row 60. And VCC is going to be a long one over there. The output is going to be on row 60 there, and is going to come round to here. So, and then we won't wire up this quite yet. This pin 1 here though is, this one is ground. What we'll just do is to hook this up to ground here, so we don't forget that one. We're just going to wire that up across the middle there. There we go. Okay, so just makes it easier than trying to wire it around to that side. So the ground on that is connected okay. So now what we need to do is to hook up all the various wires and things. So what I'll do for that is I won't commentate that. We'll just record it and speed it up so that once we've done all of the wires and ticked them off here, we'll then come back. So I just realised if we try and put the serial TTL adapter in the way around according to the schematic, it doesn't quite fit. So we're going to leave it like that and update the diagram. Just going to wire in the clock signal into the divide by 6 counter. Then we need to hook up the divide by 6 signal into the 2 clock inputs. Just plugged in the oscilloscope here, so you can see that we're looking at the output of the 3.6 megahertz clock. If we just have a look at the DSO oscilloscope application, we can see that we've got a square wave down here. It's 3.683 megahertz. So it's not quite 686, but it's within the tolerance. And on the peak to peak is 5.84. So you can see there's a little bit of overrun here at the top. So that's the 3.6 megahertz, but it's still pretty good signal. And if we now move to the output of the divider, so this should be around 600 kilohertz. Just plug that in there. We'll just change the horizontal scale on the oscilloscope. If we see now, we have a frequency of 614.439 kilohertz. That's very close to what we expect. Okay, we're just going to speed this up. So we're hooking in the address line for the register select, tie the chip enable signals to 5 volts that we don't need, and this is putting in the Y5 chip enable line, so that makes it selected at 5000. Put in the interrupt line, put in the labels on the USB serial adapter, just hooked up clear to send to data terminal already, the read write and enable signals. Then we're going to be hooking up the receive to transmit to receive, request to send to clear to send, and then we're just going to put in the D0 to D7 lines and then check everything off on the diagram. Okay, so that should now be complete. We've wired in the USB TTL serial adapter. The only issue is in my diagram here, I had pin 1, which is ground, over on this side. Probably need to reverse it, so I think the socket will need, symbol for the socket will need to be changed because of the way how it works. But other than that, everything else is wired up. Got some labels there, so you can see DTR, receive, transmit, 5 volts, which isn't connected to anything, clear to send, and ground are the way how those are going. So, as I said, all these sorts of things, sometimes you have to adjust the layout in the event of doing it in reality. So we've now installed the serial port on the Nanocomp breadboard, and in the next video what we're doing is writing 2 simple programs, one to send data from the Nanocomp up to the PC over the USB port, and the other to be able to send software from the PC down to the Nanocomp into Nanocomp memory. I hope you find this interesting. If you don't want to miss out on future videos, please hit subscribe, and if you found the content useful, please hit like. It just helps to push the videos up the rankings so the more people can get to see them. Thanks for watching.